concentrates.
Okay, I want to welcome everybody to the last Research at TTIC meeting this quarter. I'm standing in for Nadi, and I am not going to try to channel Nadi. Instead, I'm just going to introduce Madhur, who has learned to love polynomial random matrices.
Yeah, the love has a question mark, so I sort of worry less about them. I'm not sure I love them yet, but I'll tell you a little more about them as we go along. And since this is a course for first year TTIC students, this will feel like a little bit of an extension of a toolkit lecture. I apologize to the experts, but hopefully there'll be something interesting even for people who have already finished their first year of grad school. Okay. And yeah, goes without saying, just stop me whenever, at any point if you have questions. Okay, and this is the work I'm going to present, which I'll actually get to later, sort of the research motivation and sort of the exact research question, but this is joint work with Gautam Rajendran, who's right there. Okay. Okay, so let's start with actually a lecture of toolkit. So the question of what do we mean by concentration, and let's start with a simple example. So let's think of scalar as in just sort of a function map, sort of taking real values, no matrices so far, and just let's say we consider the simple function, which is sum of n independent random variables. These are Bernoulli random variables, so sort of 1 with some probability, 0 with some probability. And a concentration inequality, like Chernoff bound, will tell us that f deviates only has relatively small deviations from its expectation, or is somewhat concentrated around the mean. Okay. And we can calculate the probability of how much deviation it has, etc. This has perhaps seen it, applied it, used it, etc. Okay. This is just a set of notation. Throughout the talk, I'll be referring to, have my variables, which again in the talk I'll take as independent random variables x1 to xn, and I'll just kind of refer to the whole tuple as x. X will always be a collection of n independent random variables. And actually, I'll only restrict to Bernoulli Rademacher throughout the talk. Rademacher, just to remind you, is plus or minus 1 with equal probability, again independent. And we have a concentration inequality, which also tells us that if you have, again, sum of random variables, maybe even a weighted sum with coefficients, mean is 0 and it doesn't deviate too much. And the deviation kind of can be understood by maybe knowing this variance, which in this case just depends on the coefficients. Okay. Everybody happy so far? All right. And I mean, regardless to say, this is sort of quite useful. It has lots of applications, and these are just applications which are probably taught in TTIC courses. So there's a large number of applications to analysis of randomized algorithms, statistical learning theory, the probabilistic method, and if you've seen some to coding theory, UV teaches geometric geometry, and so on. So these are just a lot of applications which you might already have seen. And in case you want to see more applications, of course, there are sort of excellent references. There are great textbooks, including some by people at TTIC, and I kind of refer you to these. I highly recommend these books in case you want to learn more about concentration inequalities, just in the scalar sense. Okay. All right. Now let's still stick with scalar inequalities, but let's change the question a little bit. So now, earlier we were looking at f of x, which was either the sum of n independent random variables or a weighted sum, so a linear function of independent random variables. Okay. And now, let's just think of a polynomial function. So f is now, let's say, a low degree polynomial. The degree of the polynomial will always be capital D, and mostly, if I don't mention what kind of variables I'm looking at, just assume Rademacher, so plus minus 1 with equal probability. But I mean, on this slide, sort of the results I mentioned kind of apply much more generally, but in particular, you can always keep that Rademacher example in mind. Okay. And let's think of a polynomial as sort of let's think of a monomial as x to the alpha, where alpha is, this is just a shorthand for a notation, where alpha just tells me the power of every variable. If it's Rademacher, the power only needs to be either 0 or 1, because when you square Rademacher variable, you get 1. So let's just think of this as a multilinear polynomial for Rademacher variables, and you can ask, what can you say about concentration of this sort of polynomial? And there are lots of results known. This is a huge area. There's work of Kim and Wu, which uses some sort of martingale arguments. There's work of Latala, Schudy and Spiridenko, Adam, Jack, and Wolf, which uses some Poincare inequality. So there are lots of results. Each of them apply to maybe a different collection, not necessarily independent. These results are more general. And they give you concentration results based on the properties of the polynomial, etc. Okay. Any questions about the setup? So F is just a polynomial in n independent random variables. We are still interested in the question of how far is it from its mean, let's say. The same kind of question we've been looking at in the past couple slides. All right. Okay, and let's look at a specific example just to sort of reorient ourselves. So for now, let me think of Bernoulli variables. This example sort of makes more sense in that setting. And let's say the variables are now indexed by pairs. So capital N, which is my number of variables, let's think of as n choose 2, and so I'm little n choose 2, and they are indexed by pairs I, j, which I think of as pairs of vertices in a graph. Okay. And xij is 0 or 1, and 1 with probability p. So this is basically a random graph in which every edge occurs independently with probability p. And this polynomial is just counting the number of triangles in this graph. Okay. And it's a classical question with a lot of work on just what kind of deviation you can say about, show about number of triangles in a graph. Okay. And I mean, this is not an exhaustive list. I'm just mentioning a few references. And I mean, and you can ask the same question, of course, about any graph, and then the story is even more interesting when you start talking about general graphs. And for triangles, sort of Chatterjee kind of gave basically the optimal bound, even giving the right sort of constant, right dependence on p, including the log factor, which was sort of a little tricky to get in previous methods, and so on. But these are, I just want to say that these are very sharp results that are known about this kind of question. Still not, I think, I'm not necessarily up on the current state of the art, but from what I understand, maybe the results don't always go for p, which is very, very small. So if you're really interested in p as 1 over n as opposed to 1 over root n, there might be some difference in the results. So last I checked, kind of the results go up to p as 1 over some power of n, but the power was not necessarily 1, something less than 1. So, okay. But a lot of methods are known. It's an interesting question, even for this very specific polynomial, and it's a highly non-trivial question to kind of get the right kind of concentration. Okay. And also, I'll just introduce this notation of xij, which I'll come back to, so maybe hopefully you kind of remember variables indexed by pairs of vertices in a graph. Okay. Any questions about just this example? Okay. I mean, yeah, Chatterjee has a paper which is about the missing log in large deviation bounds, which also has some history of various methods and so on. He also has multiple books or like surveys about it. I encourage you to take a look if you're interested in this sort of stuff, and we can talk more later. Okay. And let me just sort of give one result, which is the result of Adam, Jack, and Wolf as a representative result. Again, I don't need the specifics of this result, but it sort of has the following flavor, that if you want to look at a polynomial and understand its deviation from the mean, it has some tails, so the probability of deviating by amount t is some exponential in t. There is an exponent which, and there's something it's divided by, which is kind of the analog of variance for linear functions. And the result is a bit complicated to state. It's sort of the stuff that appears in the exponent is the worst of some 2 to the d bounds, which depends on kind of norms of some matrices which are constructed, or norms of some tensors which are constructed from this polynomial. So you think of the polynomials coefficients as forming some sort of large dimensional tensor, and you define various norms of this, and then one of these norms appears. And also, the way I'm kind of presenting it, I'm cheating a little. The choice of A and B is coupled. It's not that you choose them independently. So this is the flavor of the result, and I'll maybe talk a little more about things of this flavor for matrices. Okay? But just, yeah, this is not precise. The sort of exact result is slightly involved, but is a kind of rough form of the result okay? Fine. And again, this result is fairly general. You can think of Rademacher, but it applies more generally. In fact, they don't always need independence, etc. for these results. Okay. Now let's get down to matrices. So let's consider a similar question to what we saw before. We have a function. This time I'm using capital F, which is a function of independent Rademacher random variables, okay? But it outputs matrices. And the way we will think of it as outputting matrices for now is we have some fixed matrices C1 to Cn, and we just multiply them by the appropriate variables. So it's a sum of n independent matrices. Okay? And the way I defined it, the expectation of this function is still 0. And now we are trying to ask, okay, how much does it deviate from the mean? Okay. Of course, when we have matrices, the definition of much needs to be quantified, like how much we have to talk of some norm. And a common choice which I stick with throughout the talk is spectral norm, so which is the largest eigenvalue or the largest singular value of a matrix. I mean, essentially, things that I'll talk about will always be Hermitian matrices, except maybe at some point. And usually, there is a simple trick in this sort of setup to go from non-Hermitian to Hermitian matrices by just considering what's called the Hermitian dilation, where you sort of put the non-symmetric matrix and its transpose in off-diagonal blocks. It's not a big deal, but yeah, you can think of Hermitian matrices if you want throughout the talk. Okay. And there is a similar result known, which is the matrix Hafting inequality, which tells you that the probability of deviating by an amount t in the spectral norm is again exponential in t squared, sort of scaled by the variance, where this quantity, which is the spectral norm of the square sum of squares of all these matrices this time, serves as the variance. And there is a factor d in front, which is the dimension of these matrices, and that's necessary because even for the special case of diagonal matrices, you basically have d separate polynomial concentration questions, and at least in general you can't avoid union bound kind of loss. Okay. So yeah, maybe for some very special functions you can say more, but in general at least this is it. Okay. Any questions about the terms or the expressions here? Well, so, and in general, a lot is known when you are trying to look at this sort of expression. So recall the expression we had was so x1 to xn are scalar or even Rademacher variables, and then you have matrices. So if you look at a single entry of this matrix, which I'm just going to use this notation, square bracket indices denoting the entry I'm looking at, it's a linear function of these variables. Okay? And there are many different settings, and a lot of very nice inequalities are known. And again, this is a great book to refer to for information on matrix concentration inequalities. Again, a very nicely readable book for the material and also the writing style. I highly recommend. Okay. Any questions about the setup? Okay, and now let's sort of get to the question which you might have guessed from the title of the talk. I want to look at a similar setup, But now every entry of my matrix is not linear, it's a polynomial in these variables x1 to xn. Okay. And I'll mention a little later where this shows up, etc. But to start with, I just want to define that sort of every entry is a polynomial, a separate one. So you can choose an arbitrary polynomial for every entry. I just require that there is a degree bound which is the same for all of them, is at most degree d. Okay. And okay, the question is the same. In terms like how much does f deviate from its expectation? Again, in spectral norm. So the norm I'll use will be spectral norm throughout the talk. Okay. The question, okay? Right. And what can we say about this? Well, I don't know. We'll see it through the talk, but in general we don't have very good methods to do this in generality. And then now we do maybe, but I'll talk. So we don't know exactly what to say. And I'm lying a little bit. It's not that we know nothing. It's we know something, and this is the kind of one technique that is commonly applied, and there's others which sort of we develop on. But in the problems that I'll mention, what is usually done is you sort of start with what is called the trace power method, where it's true that if you are just trying to look at the, let's say k is even, and now you're trying to look at the largest singular value to the power k in expectation. So f is still random, f is a function of random variables. Of course, it's less than equal to the sum of the kth powers of all singular values. The k is even, you added a bunch of, and singular values are also non-negative. And this is just trace of some power of the matrix. Now, so if you can compute the trace of some power of the matrix, you will have a bound. And this is something we talk about in toolkit again, that basically a lot of concentration inequalities are just applying Markov's inequality, and that's what we are doing here. We are trying to compute expectation of some large power of the quantity you want to estimate. If you can get a good estimate, you will apply Markov's inequality and get a concentration bound. And k, we will think of as roughly log n to get really good bounds, so k will actually be growing. But even for large finite k, this can give interesting concentration results. Okay. All right. So then, how do we compute the trace? Again, so in settings where it's applied, usually you try to interpret every entry like some combinatorial pattern. Again, if you just think of a graph, then every entry is an edge in a graph. And you can think of, for large k, fx to the k as a collection of walks in a graph, and in general, some sort of clever combination of patterns. But these patterns can be kind of overlapping, they can intersect, so there's some interesting combinatorics to be done there. And you use this to try and estimate this. Okay. And easier said than done, but I don't always know how to do this. So that's an approach which is used in a lot of applications, and I'll mention applications in a minute. And I want to try and maybe come up with some slightly more general way of doing this without necessarily this combinatorics happening. Okay, so let me now mention a couple of motivating applications and say why this kind of polynomial random matrices show up or where they might be interesting. So mention two motivations, one from sort of algorithms perspective, one from complexity. On the algorithmic side, the motivation is spectral algorithms for various kind of signal recovery tasks. So you have a tensor and there is a random spike in some direction, you want to recover it. Maybe you want to decompose a tensor into some components. Maybe you want to find a hidden vector in a subspace in some real spaces. And I'm not going to the specifics of the problem, but in a lot of these, what you usually do is the algorithm at the end of it comes up with some collection of random variables which I'll think of as sort of indexed by sort of modes of a tensor, or they're just kind of sitting in some large dimensional array if you want. Not large, 3, 4, something like that. Okay. And then you sort of combine these random variables in some interesting way. And in general, tensor networks are just kind of a language for saying how you are combining things. So in this, every node is basically just an array Okay, the dimension of the array is just the number of edges going out of that node, the number of modes of that array. So A is a matrix, it has 2 edges going out of it. B is a matrix, it has 2 edges going out of it. And this diagram just sort of says that the black edge between A and B, I kind of just look at the corresponding index in A and the corresponding index in B and sum over that index. So the black things are summed over. And now I get a new matrix where the rows are indexed by the kind of blue edge and columns are indexed by the green edge. So it's just matrix multiplication. It does it in a fancy way. So this is just a tensor. I mean, again, it doesn't matter. I'll not be using this language a lot, but it's kind of nice to know. It's a sort of relatively neat way of writing down algorithms. And yeah, in particular, there is this nice paper of Moitra and Wine, which shows how to derive a lot of spectral algorithms using tensor networks. So again, take a look at the paper if you want to see more. There are also very nice talks. Okay, and this is a slightly more interesting example where I'm thinking of two sort of array with 3 modes or 3-dimensional tensors. And one sort of face I'm just kind of multiplying and summing over, and then this tensor has 2 faces left, same on this side. And these are just 2 copies of the same tensor, not 2 independent copies, just 2 copies. Okay. Yeah, there's a question. Yeah.
How do you define other operations on tensors in this?
I don't. So this is, I mean, in general, a way of writing how to multiply tensors. You can multiply tensors with different number of modes. So you can multiply it with a vector, which is just a 1-dimensional tensor. But I can't really say, sort of define tensor PCA in this language or in general. So it's just a convenient way of multiplying things.
Or even just addition.
Sorry?
Even just addition.
Oh, addition you kind of just literally write with a plus. There's nothing in that. Okay, and here there are 2 blue edges, each corresponding to a sort of index set of size n. So in the spectral algorithms, I'm usually interested in the eigenvalue or singular value sum matrix, and what you get is basically you kind of quote unquote flatten out this tensor, or you sort of put both of these together as indexing the rows, both of these together as indexing the columns, and you sort of think of an n square by n square matrix. This is roughly there's simpler ways of writing this particular kind of tensors, but then there are more interesting tensors that show up in later works where it's harder to write them in kind of explicit expressions, and these diagrams are convenient. Again, I don't need to use them, but these are just sort of, and it's sort of maybe already clear that if I look at this example, if the entries of A and B are random variables, then the entries of this matrix are degree 2 polynomials. The entries of this matrix are also degree 2 polynomials. The entries of this matrix, if U is a vector consisting of random entries in this, there are degree 4 polynomials, and here there are degree 10 polynomials. So there's some low degree polynomials, and you have a matrix which you obtain out of them. At the end of the day, you are interested in estimating the spectral norm of this matrix at the very least, but maybe some more things and so on. So these are the kind of low degree polynomials that show up in some spectral algorithms. Okay. Questions? Okay. I mean, yeah, this is just an elaborate thing to show that low degree polynomials show up. I'm not really going to use this particular polynomial anyway. Okay. Now let's get to the second motivation, which is perhaps sort of more from the complexity side and things which are closer to. So these are so-called sum of squares relaxations. So this is a family of convex relaxations for various combinatorial problems and statistical problems. And in particular, we are interested in sort of understanding how powerful are these relaxations, what do they do on inputs, and more importantly on random inputs, or sort of inputs coming from some distribution. Okay. And usually when we try to sort of prove a lower bound, so we want to say that there is some distribution on which they do not go very well, we will say, okay, and a motivating example is planted clique, sort of analyzed in this paper of Barak, Hopkins, Kellner, Kothari, Moitra, and Turchin, where you sort of set up some, so you look at planted clique in the random graph, Gn half, where you can again every edge occurs with probability half. You can think of it as a Rademacher variable, and it's the same question. That what is the size of the largest clique? You write some relaxation for it. The relaxation sort of searches over some kind of positive semi-definite matrices, and the goal is to say that okay, the relaxation does not do very well if you're trying to show a lower bound. And what does it mean to say it does not do very well? Well, here is in general for a Gn half random graph, the size of the largest clique is about 2 times log n. But on the other hand, the relaxation is actually has a solution which is consistent with being a much larger clique. So it doesn't really get a good estimate of the size of the largest clique. It's very far off. Okay. And how do you prove there is a solution which is consistent? Well, you write down some solution, and then you show that it's consistent. So it satisfies all the constraints that you want for your semi-definite program. This solution is something which depends on the graph. So you pick the random graph and you're trying to show this random graph, the SDP thinks has a very large clique. Okay. So there is a solution which depends on the random graph, and we encode the random graph as these variables x1, x2, which is sort of encoding your data, and the solution depends on the data. How do you show the concentration of this matrix? You don't. It's not concentrated. It's actually has a lot of low rank spikes and components. So there's a lot of work that needs to be done in sort of figuring out some good pieces which are concentrated, and these are so-called the atomic pieces which exhibit some nice kind of concentration behavior. And the sort of mechanism for proving these sort of breaks this into these atomic pieces and then understands the concentration behavior for each of these atomic pieces. These are still low-degree polynomials, entries of these. And so, and I'll say a little more about what they look like, but the goal is to get relatively precise norm estimates for each of these atomic pieces to be able to understand this solution. And let's start with a simple example. Again, let's go back to our variables edges, sort of indexed by pairs of vertices. And now this time let's think of a matrix where the I and jth entry is just xij. Okay. And let's think of xij as plus minus 1. This is nothing but maybe up to a slight shift, the adjacency matrix of a Gn half random graph, with some sort of shifted by all ones or something. And I'll sort of, for a reason that will become clear, I'll kind of think of it as the graph matrix corresponding to this very simple graph, okay, which is an edge. And so it's relatively easy to sort of maybe check that the spectral norm of this matrix is about root n. And the questions that come up in this sort of semi-definite programming estimates are somewhat fancier versions of this. So let's look at this maybe. So here, let's think of a matrix where the sort of rows are indexed by I, columns are indexed by J1 and J2, let's say a subset. And I'm going to think of this sort of graph where I have these vertices corresponding to whatever is appearing on the row and columns, and the entry corresponds to the edges of this graph. So there were 3 edges in this graph between ij1, ij2, and j1, j2. So I have a product of 3 entries. In general, you could have any graph here. If I could really partition the vertex set of that graph into 2 subsets, one will be indexing the rows, the other the columns, and here I will have a product of whatever appears as edges. In general, this can also have free terms, so it need not be that everything is appearing either as a row or column. So these are like flags, basically. And and there might be free things here which I'm summing over. So I will have a summation over some monomials here, which is just summing over things which are not fixed by the row and column index. And this is a matrix. I can define this matrix for this graph, generalized to sort of arbitrary graphs. And in general, for this sum of squares, you need to analyze these kind of matrices for general graphs and then kind of corresponding. So that's why I would say you can think of a combinatorial interpretation of every entry of this matrix. And then maybe when you look at powers, it's sort of how these triangles fit together, how they intersect, and so on. That kind of combinatorics shows up. And the question you are interested in is what is the spectral norm of this? there are generalizations of these things about Gaussian things when you are not thinking of G and half, but some random sparse G and P, and so on. So there are variations of these things that show up. And there is a nice paper of on Mitla and Putichin, which is a kind of an expanded version of an earlier paper, which does lots of computations and it talks about applications of graph matrices and how to work with them. Okay. So these are a couple of examples where low degree polynomials naturally show up in the entries of a matrix. And now I'm interested in sort of understanding what can we say about the spectral norm of such a matrix. Okay? So let me kind of mention the result briefly. I mean, this is sort of, there's a more general result, but let me mention one version. And let's think of, again, let's stick with Rademacher variables, so plus minus 1. Let's think every entry is a degree D polynomial. And I'm still interested in basically applying Markov's inequality, so still interested in understanding the trace of some power of the matrix. And if I can do that, then I'm home by Markov, basically. And what we show is that just like the result of Adam, Jacques, and Wolf, you can understand this quantity in terms of the norms of, again, exponentially in D matrices. So these matrices are indexed by pairs A and B, which sum up to some number less than or equal to capital D, and I'll say what these matrices are in a minute. But importantly, these are expectations of some random matrices. So these are fixed constants. There is no randomness here. Okay? And I can understand this by these constantly many matrices which have no randomness in them. Okay. And this matrix is actually relatively simple. It's just think of it as a matrix of partial derivatives. So f is a polynomial. It's some function. Let's say I and j are indices of my original matrix. Let's augment these indices. Let's maybe put a few variables. Let's say the names of a variables in the first index and the names of p variables in the second index. Okay? And the entry is just when I take the derivative of this polynomial with respect to all these variables, all the ones that appear inside alpha, all the ones that appear inside beta, a plus b total. So it's a derivative with respect to some a plus b variables. Okay. This is Rademacher, so things are always multilinear. You cannot differentiate with respect to the same variable twice. And so alpha and beta can be disjoint, otherwise this is just 0. And so this is still a random matrix. It's a function which is obtained by taking a derivative of the original function. Okay. But what I'm interested in is the expectation of this function. That's it. That's sort of the result. I'll say a little more about how to prove this, etc. But is the statement of the result roughly okay? And I have to say, just sort of, even for scalar, we don't always know results which maybe can just avoid this entirely. So you do need to look at some slightly intricate properties of your function, and here we are looking at matrices. But these give, I mean, it's not that I can give one paragraph proof of some of the previous results, but it gives at least significantly simpler proofs or shorter proofs of some of the results. Okay.
So, yeah, Madhur, just a quick question. So can we recursively actually apply the same inequality?
Precisely. So in fact, I'll actually, so here, I mean, this is already an expectation. So this is constant. There is no randomness. So,
but then you can use the upper bound using trace.
For a constant matrix, I can't quite do this because the derivatives will be 0. It's,
I mean,
so you want to apply this bound on this matrix, right? Here I'm saying the expected trace of a random matrix is upper bounded by the trace of some fixed matrices. And in particular, if you take A and B to be 0, it's the expectation of the original matrix. That term is sitting here. For this, because this is a polynomial of degree 0, when I try to do recursion, I will actually just be stuck at the expectation of this matrix anyway. Every derivative will be 0, every non-trivial derivative. And I'll just be stuck at the term which I'm still looking at exactly the same matrix, which is its own expectation. But I'll actually derive this proof using recursion on a simpler argument, so we'll get to that. So recursion is useful. But this is what I'm showing you is kind of already the end point of the recursion. So, I mean, this is why I'm going up to degree d, because after you take a derivative d times, the polynomial just vanishes. There's not much else to do.
So there are some conditional expectations in the middle that eventually...
Exactly. We'll get to that in the next slide.
Look, as far as I remember those previous results, one way of proving them is to consider the exponent instead of sufficiently high power of the polynomial.
You mean some sort like e to some...
Yeah.
Right. So there is... I mean, we don't sort of... In the next slide, I'll kind of show what is the sort of workhorse of this, which is some sort of Efron-Stein inequality. There is an exponential version, and you can work with exponents.
Can you prove analogs of your result for the exponential version?
I mean, actually, if you're allowed to work with, I mean, you can take this power k to be large enough, so it actually gives the same sort of power as the exponential results. So, I mean, okay, it's possible. Okay, in short, it's possible to do the exponential version. We work with this one just because it's slightly simpler for us. But yeah, I mean, the proof is not, as you will see, the proof idea is not complicated, and you can use a different version of this inequality, which was proved in this very nice paper of Pauling, McKay, and Trop. Okay, so to get to it, the key technique we use is so-called matrix Efron-Stein inequality. And I'll mention sort of the details in a minute, but this is a very nice paper to read of Pauling, McKay, and Trop, and in general it uses this very cool method of exchangeable pairs, which has had a lot of other applications, including a lot of Chatterjee's work. It was sort of the kind of behind this method to a large extent, although the method is called Stein's method of exchangeable pairs, so it has a longer history. In what the inequality does is kind of, it sort of tries to understand this function f by understanding how it responds to local changes. So if I look at f versus this f superscript I, where f superscript I is exactly the same as f, but I've resampled the ith input. I've just put it in an independent copy. Everything else is unchanged. I've just changed one bit. Okay. And we are summing over these sort of local changes. So if this was a scalar Boolean function, you would call this the influence. And so this is a kind of fancier version of the inequality that the variance is upper bounded by the influence for a scalar Boolean function. And what this inequality says is that if you are interested in understanding the moment, so I have to say, this is the matrix version of it. The scalar version of it was already known by Boucheron, Lagossi, I think Massard. And they also get exponential versions of it, and also kind of more refined versions where you can sort of refine this variance quantity a bit more. And again, a very nice paper called Concentration Inequalities using the entropy method, which develops some of these arguments. For matrices, the version I'll sort of use in the talk is that if you are interested in understanding the trace of f to the 2k, you can look at this sort of, some kind of a proxy for the variance, which is this influence kind of version. This is still a random matrix, it's a function of x. All I'm saying is that if I keep x fixed, resample the ith input to the function, what is the expectation of the square conditioned on x? So only the expectation is over only the sort of bit I resampled. And so this is some still random matrix, but I can upper bound the expected trace of this with the expected trace of this, and hopefully this is simpler if I'm only analyzing local changes. And you can already guess this will show up with partial derivatives based on the shape of the result. And yeah, as Raj said, basically use this recursively. So this will give us some sort of one step of the recursion, and then we.
Just to make sure I understood the source of my confusion. So if I resample everything, then we get to the right-hand side that you showed us.
Yes. Yeah.
Do you still assume here that K is even? Because otherwise it
No, here I wrote 2K, so I kind of did away with that assumption.
In the right-hand side, it might be 0.
Yeah, but I won't need it. Well, okay, it might not be 0, but
It may not, okay.
yeah. Right? It's
Well,
and K is non-zero, but even if K is 1, this is still 2. 4K minus 2.
V of x has
K
positive entries, right?
V of x need not be positive entry. It's a square of a matrix, but the square of a matrix need not have non-negative entries. This is the power of a matrix. So, but okay, I'll resolve that issue of this K in a minute for
Okay,
V of x.
good.
Yeah, we'll get to that.
Let's postpone it.
I'm just curious, how old is this inequality?
This one is 2016, so
Okay.
relatively recent. So I think there was an earlier paper, maybe from 2012. Don't remember all the authors, but again, McKay was one of the authors, and then Michael Jordan. It was also you trying to derive the kind of linear versions like matrix half-Ding, maybe some sort of concentration results for some nice degree 2 polynomials and so on using exchangeable pair method. And this one is a more recent application where they kind of get results. Again, this inequality works in general, and this inequality is not limited to polynomials. But for polynomials, there is a nice endpoint to your recursion. And yeah, I'll say more about it. And then there are also later generalizations which I'll mention. Okay. Now let's just do one step of the recursion or try to understand what it does. Forget about matrices, let's just try to do the recursion for a scalar polynomial. So we just have a function of n random variables and we just try to do this. Okay. So let's think of a scalar polynomial. Let's assume that the expectation is 0, not worry about it. And now let's try to look at what this v of x looks like. It's actually just kind of expectations over local changes. So let's say what happens when I change the ith input in f of x. Okay. For every alpha where the ith input doesn't appear, it just won't change. So the difference, it just won't appear in the difference. It will just cancel out on both of these terms. The only alphas that will appear are the ones that actually contain the ith bit. And
so you assume multilinearity? Oh, because
I'm assuming I'm sticking with Rademacher. So yeah, but otherwise you can do this without. Yeah, you'll have to work with multi-indices. And now this x alpha minus I is just my notation. You kind of this alpha is a bunch of variables. You remove the ith variable, so it's basically the derivative with respect to the ith input. And then you get xi minus x tilde I, which appears with power 1 in here, not 0, and you get the square of the whole thing. Now the expectation again is only with respect to x tilde, x is fixed. So the only thing that, so this thing doesn't really show up in the expectation, the only thing that is inside the expectation is this very simple quantity, which is actually just 2 in expectation. Right? So it's, so you can write this v of x as this sort of very simple matrix times its transpose, where the ith entry of this matrix is just the partial derivative. This, so we already saw some sort of expansion of our matrices. We started with a matrix in 1 dimension, and we ended up with matrices which are at least row vectors or column vectors, depending. So we augmented the index set a little bit. This will keep happening. It's, but I have to say that this sort of equality for Rademacher variables is particularly convenient. Sounds like a trivial thing, but most of the technical work was actually trying to work with general product distributions where because this is not true, the recursion actually stalls. The factors, like the left-hand side appears as a term on the right-hand side, and with a bigger constant in front of it, naively applying the recursion. So we sort of get stuck if we don't have Rademacher, but I'll say a little more about that. Okay, but sticking with Rademacher, this is okay. We just kind of wrote v of x as, forget the 2, some matrix times its transpose. Okay. Actually, I think I defined v of x. I think their definition has already a half built in, so this 2 also doesn't appear. Okay. So now, this v of x, recall we sort of already derived this expression, which I'll just say is some matrix times its transpose. This matrix is really what I was saying. I augment something to the row or column index, and I write down partial derivatives with respect to whatever is the augmented stuff in the index. In this case, the name of one variable, okay, some I. So this matrix is just a slightly bigger matrix. And now if we look at the inequality, it gives us this expression. As I said, maybe with a little bit of manipulation, you can basically think of this as the square of some matrix where this sort of thing stuff is. And so this k again becomes 2k when you think of the matrix, the square of which contains this term. And so this odd even issue doesn't arise. We start with 2k, we basically stay with 2k. So it's not a problem in this inequality. Okay, we apply the recursion on this f10 or some sort of Hermitian dilation of f10. So that's the thing we use in the next step of the recursion. Okay. So it's very simple. At one step of the recursion, we took the derivative once, we keep repeating. We can only do this d times. At the end of d times, we just sort of collect together whatever you got, and that's your bound. Okay. And it's a relatively easy bound to compute in sort of various applications. It's not too crazy. It requires some little bit of case analysis. It's not one line, but it's not too bad. Any questions about the proof? Okay. Now let me say there are a few extensions.
Can I say
Yeah,
much about
please.
the results? So, do you know if the dependency on k on the right hand side is kind of like tight in some sense?
Not sure, but I think the same sort of dependency also appears in the scalar Efron-Stein. It's this dependency will give you this extra log factors, which are a lot of source of lot of annoyance in concentration bounds. I don't know how to get rid of it in general, but at least the Efron-Stein route I don't think is going to get better.
My understanding is in the case of a scalar, you have just the exponential function, like constant to the power k, not linear function to the power k. Or
I
maybe
thought it was still k to the k, at least the version I remember. But okay, we can probably try to dig it out after. Okay. As I said, I mean, much of the technical work is actually trying to extend the framework of Polynomial and making this sort of recursion work. In general, the problem is if you try to naively do the recursion, because of the fact that the expectation of xi minus xi tilde square is not 2, but actually something which depends on xi for general variables, you will end up, even if you think of, let's say, p-biased, sort of a sparse random graph, in general, the right-hand side will already contain the left-hand side as a special case with a larger coefficient, so the bound will be sort of trivial. And you have to kind of modify their proof to sort of inside the method of exchangeable pairs to sort of somehow add a way of remembering what are the variables we've already differentiated upon and not including them in the bound. So this requires a bit of work. With this, you can kind of derive the results I mentioned, also results in the so-called sparse graph case where you're thinking of maybe not g and half but g and p, but again written in a way that scaled appropriately so that the variables have mean 0 expectation 1, which is convenient. So sometimes they're 1 over root p, sometimes they're square root of p minus 1 over p with some signs. So, and these sort of results were also derived using the trace method concurrently. Wouldn't say independently because authors are a subset, but with Chris Jones, Aaron Purichin, and Jeff Shu. I mean, in some sense, yeah, sort of Efron-Stein method gave us the guess for the right kind of bound, and once we knew what bounds to aim for, you could also derive it using trace method. Okay, but at least I'm less worried about polynomial random matrices because now there's at least a generic hammer I can try and apply.
if you replace independence with negative correlation.
Great. So I don't know that yet, but there are extensions of Efron-Stein inequality under fairly generic conditions, basically using some sort of Poincare inequality, which is also not quite the same, but sort of similar setting where the Adam, Jack, and Wolf result works, but they can handle Poincare inequality in some LP norm where this is L2 specifically, and but you do need some kind of nice mixing Markov chain, and so there are sort of extensions of this result. It would be nice to see if the whole argument can be extended. I suspect it should be doable, so maybe a little more care in terms of writing down the arguments. But yeah, so far it's not at least written for non. But I think it's possible to go beyond independence, particularly using this sort of new Efron-Stein inequalities. Okay. The other, which we already alluded to, is that it's sort of off in log factors, polylog factors. I mean, for the kind of questions, these don't matter in some sense. It was not always clear how to get just the right polynomial exponents of n even, and so it is useful to get some bounds, but I think they're not the sharpest bounds, and sort of some analog of maybe the chaining method combined with this would be nice. I don't know that yet. The third, which I like, is maybe some analog of so-called hypercontractivity, which is maybe a quick and dirty way of proving concentration for scalar polynomials. So hypercontractivity just tells you that for degree d polynomials, you can bound the 2kth power by the second power with some things in front. Okay. There is no 2 to the d matrices appearing, nothing. It's just in terms of the variance. Okay. It's not always the optimal bound. It can be lossy. But it's at least some good bound. Which can, again, if you take k to be logarithmic, you can derive exponential tails just using hypercontractivity. There is a nice write-up in Ryan O'Donnell's book in case you want to take a look at it. So it's a fairly easy way of deriving concentration inequalities, at least if you don't care about the very precise exponent, but just get some form of concentration. I don't know of an analog of this result for matrices. I mean, there are some so-called matrix hypercontractivity results known, but I mean, in matrices, you have to be a bit careful about, like in hypercontractivity, you can sort of state this, or you can state some sort of dual version of it in terms of norms. In matrices, there's sort of two kinds of norms. One is the norm of the function under which you are computing expectation, and second is the power of the singular values that you are considering, which are slightly different. And these versions do not seem to give this even when you try to use duality, etc. So I don't know of a matrix hypercontractivity inequality which actually gives concentration. This would be nice to figure out. And I mean, of course, if you can find more applications for this, I'd be happy. And I'll stop there. More questions?
So we had quite a few questions during the.
I'd say, I mean, even if you forget everything in the talk, just remember this sort of Efron-Stein inequality for matrices. Take a look at Pauline McKay-Tropp paper. It's a really nice paper, a very simple argument. I mean, especially if you're restricting yourself to polynomials, you can write down the whole argument in one page. It's very clean, very simple. It's a beautiful paper to read.
So you think of hyperconductivity as stronger than or weaker than Efron-Stein?
It's weaker. I think at least in this form, it will give you a weaker bound. But it will give you some concentration bound. I think the amount of deviation it will give you might be similar. Well, okay, it's not completely separable, but at least you can get some sort of bounds on how much f of x deviates from its mean, but the exponent in terms of this deviation t will not be the right exponent. So I think in Adam, Jack, and Wolf, I said the exponent is something between 2 over d and 2. And I think hypercontractivity in the naive form will just always give you 2 over d, never anything sharp. So it's weaker in that sense. But it's very useful to get a quick estimate in several cases. And yeah, I would like to have at least some analog for matrices.
And is Adam Jack like the best known right now? Or?
I don't know. I think that's the one I know in some sort of under most general conditions, maybe. But that's also 5 years old, and I have not always kept. But I think if you really are interested in very special cases like 0-1 variables, sparse graph counts, and so on, then you can do better. And so it's hard to compare best because you're sort of looking at the sharpest bounds and the most general conditions, and these are not always the same.
Do you know how they prove it?
Sorry? I mean, so we had some, if you remember, like, okay, maybe in some research we discussed maybe how to get hypercontractivity using Poincare inequality. And hypercontractivity gives you concentration, right? And they are basically using Poincare inequality. So it's roughly a similar analog, but they're using Poincare inequality in some other norm rather than 2 norm, but recursive application of Poincare will give you some kind of hypercontractivity like bounds. But maybe more refined rather than the naive version, but at least a similar philosophy of the proof. It also, by the way, the matrices that appear there also have partial derivatives in them. So it's not like a completely crazy result, which is very different from what we have here. But the proof is maybe if we kind of find the right proof of our result also using Poincare inequality, it will look very similar. I don't know. Sorry.
Yeah, I'm just curious for like a scalar where we have the concentration for, let's say, Lipschitz functions. Have people studied Lipschitz random?
Right. So I think the Efron-Stein inequality applies more generally. But even for Lipschitz functions, each derivative term will be some sort of matrix bounded by a constant, but when you sum them up, it's still a fairly large matrix. So the sum of these local changes, right? So each local change will give you a small matrix. So I don't know how to kind of naively apply it, maybe. I think.
But if you have like the recursive Lipschitzness on all the partials, then...
Yeah, possibly. It's I don't know a result on top of my head. But I can try to. I mean, yeah. I think there are relatively few papers I could find on this kind of nonlinear concentration. Again, there's sort of this group of authors. There are some more general conditions, but I didn't see a general result for Lipschitz functions.
Thank you.
Okay.
Oh, yeah.
Is there anything known for matrix anti-concentration?
Great question. Yeah, so I don't know yet. It's I mean,
What was the question?
sorry?
What was the question?
Is there anything known for matrix anti-concentration? So can I prove that the probability that maybe the largest singular value of f is smaller than epsilon is very small? And yeah, I don't know. It's in fact not always clear how to properly define it, because whether you want to look at the least singular value, the largest one, or so what exactly. But I don't know of results about that. That would be interesting to study.
There is a matrix version of Littlewood offered in additive combinatorics, which is kind of...
Okay. I didn't know this. It's
I mean, it's not about like the spectral norm. But
so, I mean, Littlewood offered, at least the usual form is about just probability of being 0. And so, is it really about the singularity of this random matrix? Okay. So,
being 0 or not. Exactly.
sorry?
Being singular or not. Yeah.
Being singular. I mean, so, in fact, Littlewood offered results were used to prove the probability that the random matrix is singular or not. But yeah, sorry. I was thinking more along the lines of Cadbury, right? But I'm not sure I know a matrix analog of Cadbury.
It's much weaker than decent anti-concentration bound on the smallest eigenvalue.
Yeah, I mean, I'm not saying that nothing is known, but I can't say anything on top of my head. But I don't think anything in this sort of generality is known for matrices.
Okay. There. Thank you very much.